Hello, everyone. Thanks for joining us and welcome back to GRASP's Student, Faculty, and Industry Talk Series. This week, I'm really excited that we have our first external student speaker of the semester, Maria Bauza Villalonga. She's a fifth-year PhD student in mechanical engineering at MIT, where she works with Professor Alberto Rodriguez. Before that, she received her undergraduate degrees in math and engineering physics from the Polytechnic University of Catalonia. Since moving to MIT, she's done some excellent research in robotic manipulation, for which she's received several fellowships, including ones from Facebook, NVIDIA, and Lacacia. And she's been awarded the Best Cognitive Paper Award at IROS 2018, and also was a Best Paper Award finalist at IROS 2016. She was also part of the MIT Princeton team participating in the Amazon Robotics Challenge, which she won the stowing task in 2017 and the 2018 Amazon Best Systems Paper Award Manipulation. Today, she'll be sharing her recent work, which focuses on combining tactile and visual information to enhance robot dexterity for manipulation. So I'll hand it over to her so we can get started.
Hi, everyone. Thanks a lot for inviting me. I really appreciate it. So today I will be talking about how can we go beyond picking and how can we use different types of sensing to actually go into dexterous manipulation. So you are probably aware that if you go into a warehouse or into an assembly pipeline, you're going to see some humans doing tasks like this one, where you have some components and you just have to assemble them into some location. And the question is, why are we still relying on humans to do these tasks? The straight answer is because these tasks usually, if you put a human on them, end up being more cost effective than actually engineering a robot assembly that would do the same. So then, and that happens even when those objects are rigid and well known. Even when you know exactly how the part is going to look like and where it has to go, you're still relying on humans. So the other question is, what is preventing us from automating this task? And I will argue that there are probably 4 factors that are preventing us, because you probably want to have all of them into place when you develop a system. The first thing is that the system must be affordable. It must be cost effective. If it takes you long enough to build a system or you have to re-engineer every time you need to make a small change on your task, that's not going to be the ideal. It also needs to be adaptable in the sense that you will need to change some parts of your task. You will need to change the object that you are manipulating. You will need to change where you are actually putting them, how you are assembling them. And if your solution cannot adapt to that, then it's not going to be useful. And finally, in terms of performance, you want to be accurate. Usually when you're in assembly or in industry, you don't have the luxury of not being accurate. You need to be precise. You need to make things reliable. And that also brings us to robustness. If there is some event that you are not predicting, something that goes unexpectedly, some failure, you need to be able to detect or react to that. So usually when we go into industry, we do see some robots helping us in different tasks. Like in this case, I am showing you pancakes, or I am showing you how we build a car. And why are we having those? I think it's because they fulfill some of the aspects that I was mentioning. In this case, I would argue that those are usually very robust and very accurate. And when we see them deployed, it's because they actually can be cost efficient. But that's because the lifespan of the task that they need to solve is usually really large, so that it pays off to spend all the engineering time that we require to actually make those tasks happen using automation. So yeah, if you have a task that you're gonna be making pancakes for years in the same way, then it might pay off to build a system for them. But actually, in most of the cases that we are seeing today, is the other way around, where actually things change all the time and your production line might only last for a few months, if not weeks. So how do we build systems that can just adapt themselves to all those situations while being time efficient and cost efficient? And I think the ideal for most of us doing research on robotics is, can we find an hybrid solution that combines maybe learning and engineering? And we have seen a lot of progress in that direction, because ideally learning, what is promising to us is something on the lines of, you're going to have a system that is adaptable, that can generalize, and that is not just tailored to a very narrow task, that can actually do many more. And that's things that we have seen when we look at some advances in games, where reinforcement learning, the same algorithm can help solve many different games. But then if we want to do some more complex tasks, we're actually seeing that either we have to narrow ourselves to just very specific tasks, Or if we want to be able to generalize with the same algorithm, then we might actually lack the robustness that we would like to have in practice. So how do we go about that? I think we need to find ways so that our learning algorithms are not just affordable and adaptable, but they can also get good performance being robust and accurate. And I think there is one task where we have actually seen a lot of success in this direction, and this is speaking. Recently, we have seen a lot of startups and research on this direction. And I like to point out the Amazon Robotic Challenge, which is for me one of those that really said, okay, I think picking is ready to go into warehouses and solve the problem that right now is being done with humans, which is you're going to encounter a set of objects and you want to be able to pick them and put them in boxes or just in other bins. So solving this task has become something that actually combines learning and engineering, and we have seen plenty of startups come up from Dexnet to XYZ Robotics or Berkshire, among many, many others. And I would argue that's because we can make those solutions affordable and adaptable. They can handle many different objects. Once they are deployed, they usually doesn't take months to develop them and they can last for long. And to some degree, they can be robust. But I'm also going to argue that while picking it's nice and we have seen a lot of progress, picking itself is not very, it doesn't require a lot of accuracy. You just need to pick an object and put it somewhere else without requiring to be a lot of accurate, which is something that actually most of our solutions for real industry problems is going to be a requirement for. And I actually just want to show you my first-hand experience. With my lab, we actually participated in the Amazon Robotic Challenge. And the goal was, I'm giving you this bin, please just empty it. And this was our system. We just built in the span of a few months with just a few, 10 or 15 students. We built this system. So again, this was affordable because we just needed a robot. We just hand designed a gripper that was powerful enough, and then we just had some cameras. And it looked like this. So as you will see, we have a suction cup that allows us to go pick objects and put them in any way, let's say, into another bin. Because our only goal is, can we move things from one place to the other? Again, this solution was affordable and adaptable. We could handle a large variety of objects. We could also correct for failures. To some degree, it was robust because if you look carefully at the video, sometimes it fails, but it's able to recover. But it was not accurate. And you can clearly see this from the final state of the bin, where clearly all the objects are just messed around. And if you were to do this as a human, you would probably try to be a bit more accurate on how you leave them. But inherently, picking, I would say, is not as accurate as we would like to be. So after finishing the ARC, we were happy about the results. We really felt we could develop those solutions that were affordable and adaptable. But there was still a missing question. We have achieved something that is probably not as accurate as we really would like to have. We have still been able, and we would like to have something that can go beyond. So what can we do beyond picking that is going to give us more robustness and accuracy? It's going to force us to get to those milestones without, again, sacrificing on being cost effective and generalized enough to varieties. And we realized that there were two challenges. The first one is that once you contact an object, because again, I'm going to be talking about manipulation mostly, robotic manipulation. And when you touch an object, when you grasp it, then suddenly contact becomes unavailable. You want to change the state of the object, you want to change the state of the environment. And that means that you need to exert contact on the environment. So that was the first thing that we realized. We need to understand how to exploit contact to our advantage. The second one is that we need to find a task where we can still make our solutions affordable and adaptable, but that forces us to be accurate. And this is something that I will go through this talk. The first thing that I'm going to talk first is how do we use tactile sensing, because again, contact is unavoidable. But then I'm going to go and present you the task of kitting, which is a task that requires you to precisely pick an object, but especially to place it in a very tight space with a very specified configuration. So you have to do this pick and place very precisely. And hopefully this is going to show us that if you find a solution to this task, you have to ship a solution that is not just affordable and adaptable, but also robust and accurate, because it implicitly forces you to be accurate because the placing must be. You are told you have to place it in this final configuration. So let me first start with Tactile. And after the ARC, we were like, okay, we need a sensor that can suffice our needs in manipulation. And we had to come up as a lab with a sensor that was good enough for the task of manipulation. And here's what we came up with GelSlim. GelSlim is a high resolution sensor that you can see in the video that when you press the white membrane of this sensor, it's actually gonna give us images that show the full contact that is happening between the sensor and the object. So when you're actually working with your robot, you're going to have access to these high resolution images that give you a clear imprint on where contact is happening. So that was our first milestone. And we have keep working and improve these sensors to a state that now we are close to get it deployed to other labs. So we're happy about how it's working. And the first questions that we ask is, okay, how can it be used? And for that, the first question that we ask is, can it help us to improve picking? Can we use it to improve stability? Because we were just coming from ARC, so that was a very natural question to ask. And I want to show you this video where on the left, the robot is going to use a policy that first detects stability if the grasp is stable or not. And based on that, it will try to regrasp if the grasp is not stable. This one is just like the vanilla where you just go grasp and leave the object. And as you can see, if you apply the same grasp on the object, in this case, we detect this is not a good grasp, and we go again and we regrasp it in a place that we think is going to be more stable. And the way we did this work is just by training it on many grasps, trying to find using neural nets what was the patterns that would identify if something is stable or not, and then just apply it at test time. Then on the second part, we actually ask, can Tactile help us localize objects? Because if you think about blind people, they are doing this all the time. They don't have vision, but they can go around their houses, pick anything they need, and they can just understand where it is in their hands, just through Tactile. So that was the question that we tried to ask. And for this, initially what we did is, let's just touch the object at many places so that we can actually create this tactile map of the object that comes from collecting a bunch of those tactile images to reconstruct how the object more or less looks like if you were to touch it with a tactile sensor. And now at test time, all we need to do to localize the object is we touch it, we get one of those images, and then we try to match where this image would fit into this tactile map. And this is the way that we try to solve this problem. And yes, both of them work, but what happens is that you need plenty of real data. In this case, you had to grasp plenty of objects until you were confident to say, oh, this new grasp is going to be stable. In this case, you need to go and explore first the object to build this tactile map so that then you can go and localize it. And that's nice, but that's not going to escalate well. That's not going to allow us to use many of objects, and that's not going to be time efficient because you need to go into the environment and for each of your objects, just go and touch them. So that really meant for us a big challenge. How do we go about this? How do we try to solve this problem? And in the end, we realized, okay, can we find a way without touching the objects, without any prior tactile data, to localize the object from the first touch? And that became our goal. And that was the problem that we wanted to solve. You're going to go with your object, you're going to touch a sensor, you're only going to get this for the first time, let's say, and you're going to have to localize the object. And we said, okay, if we do an assumption, we think we can solve this problem. And the assumption is going to be, let's assume that we know the object model, which might seem very restricting, but actually, if you think about most industries, they have to manufacture their objects. So they actually have reliable models on how the objects that they are manufacturing look like. So in many cases, assuming that you have the object models, it's a valid assumption. It's something that you can actually start with, rather than saying, oh, I will be able to collect plenty of data for hours on this new object. So we went with that assumption. And this is how the results look like. I'm just giving you the results of our approach first. So again, you're going to touch your tactile sensor. You're going to just get these images. And this is how our solution looks like. So you can see how we can more or less accurately localize the object with respect to the sensor. And again, all we are using is the object model and those images. And from the first time, we can already say, oh, we think the object is in this location. So now I will go into how are we solving this problem. And it has two main components. The first one is that we need to know go from these tactile images that are high resolution into something that is a bit more tractable. And for that, in other words, we had already developed some neural network. It's very basic, but what it does is this neural net extracts, it just uses some CNNs, the contact region. So what place on the sensor the object is actually touching. And this is what it does. It just gives you an image. So it converts an image into another image, and now it's just marking there is contact in all these regions. So this is what we call the estimated local shape from the tactile image. It just tells you which part of the object is actually making contact. It just tells you what this shape is looking like. And this is everything independent, and that's important. Once you have calibrated your sensor, once you have trained this neural net, which is something very fast, you just need a few images, you can use it for any object. So you don't need to touch this sensor with this object in order to get this map. As long as you have calibrated it before, which again is a very easy process that we do it all the time. Sometimes it just requires like a few, we have all the system calibrated basically, so it's very easy. Then you can use it for any object. So this is object independent mostly. And then the second part is actually the one that uses the known object model. And what it does is we use rendering to find which are the poses of the object that would actually contact the sensor depending on the relative poses. So we simulate contact poses, and from those, we try to extract the same information. What is the part of the object that would contact the sensor? And we provide those, again, as images. So that now we have this other tool that in simulation is capable to generate the same type of simulated local shapes. The final goal then becomes, if you generate enough of those simulated local shapes in simulation, can you try to find the one that is most similar to this one? Because if you do find the ones that are more similar, because you are also going to know their poses, you're going to be able to know which is the most likely pose that has generated this image into the sensor. And this is what we call tactile image matching. And basically what we're doing here is we have, this is trained all in simulation. So we just take one of those two local shapes that we have generated and we encode them using a ResNet. And once we have encoded them, all we need to do is compute a score of how similar they are. And this just needs to be trained just to know that, again, this score, we can kind of interpret it as what is the likelihood of one local shape given that you know the pose of the object. So how likely are we to get this local shape given that this is the pose of the object? And the way we're training these encodings is by having two sets. We have a set of positive data. So those pairs of local shapes should be similar. Instead, those pairs should be negative. So in some sense, the likelihood for this case should be 1, for this one should be 0. And if you train it like this, it works really well. And basically what you can do now is, if you have enough of those, we actually built a grid of local shapes. If you have enough of those, this is dense, then you can try to find which are the most similar ones. So which are the simulated local shapes that look more like what you have in here. This is already giving you poses, but then because this is already good initialization of what is the good pose, you can do an extra step, which is registration. You use ICP or some variants of ICP to try to adjust your pose so you can go even beyond this dense set of poses that you had already pre-computed. And finally, again, because all those its poses, you can get the pose distribution. And it's a distribution because you not only get the best match, you actually get the scores or probabilities for all of the other elements in your dense set. So you're actually getting a distribution, which is really important because sometimes what happens is that you have non-uniqueness, meaning that different poses of the object will result in the same type of contact shape or very similar local shape. So in order to account for those, it's better to have distributions rather than single outputs. I just want to emphasize that computing encodings is really important rather than just making a direct comparison between images. And that's because when you use encodings, the first advantage is that you can be more time efficient because now you just have to compare vectors. And actually you can store the vectors from your dead set of local shapes. And the only one that you will need to compute is this one for this local shape that comes from the sensor. So now at test time, you only compute one encoding, and then you just have to compare those vectors, which is super efficient. You can parallelize and it's very, very fast. You just do this comparison between vectors to get all the scores. So having encodings already gives you a lot of more efficiency in terms of compute, but it also is a very nice way to adapt to the metric of similarity that you actually want to define. You are not asking, please give me the one that is more close in pixel distance, which would be something that we can just do directly with images. You're trying to ask a question, if I give you those two images, how close are they in the pose spaces? How close are the poses that actually generate those images? And that's a more hard to define metric. And that's why you need to do this implicitly. And that's how encoders and encodings help us a lot to find the easy way to actually encapsulate what it means to be close in pose. Another thing is that encodings and images are something that has been widely explored in computer vision and contrastive learning. So all the tools that we have from data can actually be immediately deployed into this system. So despite us being users of tactile information, we can still benefit from most of the tools from CV, which makes progress much faster. You don't have to come up with new tools and new networks. CV and contrastive learning already give you a lot of those tools. And finally, again, because now this is fast and it's just encodings that you have just to multiply to compare them, you are actually finding a nice way to get probabilities. And those probabilities are good on themselves because now you can add priors, you can add other constraints to them in a Bayesian framework. So this is just to motivate that using encodings allows you to get probabilities, which later you can use to improve your predictions just by you adding other constraints. We actually test that. So I'm going to briefly show an example of how we can add constraints using those probabilities. And I will do that in the case where you have multiple contacts. Let's say that now you're just not touching the object at one pose, but you're touching it at different poses. In the case where you want to compute is what is the likelihood of a certain pose of the object given all the local shapes that you have obtained for all your, let's say, N sensors and tactile sensors. And if you look into the paper, we actually show that by induction that this basically reduces to multiply all these terms. The last one is nice because it allows you to add any pose constraints. If you were to know that there is collisions, that there is occlusions, or that there is some information coming from vision, let's say, you can add that information into the likelihood of this pose. But then you can also add all these terms that you know how to compute using the similarity function and just multiply them. And again, getting those is really fast. You just need to use the encodings that we were talking before. So very easily, you have a way using these probabilities to better figure out what is the likelihood of each of the poses that you're considering. So let me go into the results. This is the first video that I show you about tactile localization, just that now I am adding what is the predicted local shape coming from the sensor together with what is the best match from the dense set of simulated local shapes. And you can see how they clearly match, meaning that we can get a good estimation of the pose. We run experiments for 6 different objects. You can see them here. And now I'm going to show you a bunch of videos for each of those objects once at a time. So here you can see all of them. You can basically get good performance on most of them. The ones that are bigger or have harder or more non-unique local shapes are the ones that we struggle the most. This is usually this object where actually different local shapes actually look the same. So distinguishing between them, it's hard, especially if you're just considering the most likely pose given from your algorithm. But overall, you can get accurate localization, which is what you wanted, even if it's just coming from tactile sensing. I'm also going to show you some quantitative results because those are important to understand how accurate your algorithm is. First, let me explain how this is going to look like. This is going to be the pose error that you're going to get when you select a random pose. Let's say I just want a pose that is in contact. What would be the error that I get if I compare this with the actual pose of the object? And in millimeters for this object, the pin, which is the one that I've been showing you all the time, you will get around 43 millimeters. And then here I'm showing you the normalized. So random error is 1, and everything below is going to be better than random error. And this is if you were to pick exactly the right pose from the dance set. Because in this case, we are going to have label data. We know both the tactile image, but also the true pose. So we can know, okay, what is, if I were to have access to a true pose, what would be the closest one in my dance set? But basically, if you use our algorithm, you get this violin plot where you can see that most of our pose errors are pretty low. So they are often way below 10 millimeters and usually are in the order of 4 millimeters, 4 to 5 millimeters. Then we can do this registration step where now we can refine the poses. And this means that we are able to improve a little bit the poses that we already had a good idea of which ones they were. But you can see that there is these bumps in here. These bumps represent this non-uniqueness. Different poses on the object will result on very similar or even the same contact shape. So there is some error that is unavoidable if you just consider your best estimate of the pose. And that's why next we also show what if you consider the 10 best. Ideally, between the 10 best proposals from your algorithm, it's likely that one of those poses that might be non-unique is going to be in there. And this is exactly what we are seeing here. This bump from non-uniqueness almost disappears because now in most of our predictions, even if there is non-uniqueness, you are going to have both instances into the 10 most likely. And as you can see, the error clearly decreases. And now it goes into the order of 2 millimeters or less, which is really good, given that you're only estimating the pose of the object from the first touch. We did this for other objects, and you can see that the pattern is the same. You often are going to have this non-uniqueness, but as you consider more samples, often it's going to decrease, not always, but it definitely gets better. But overall, what you can see is that most of the distribution of errors is pretty low and closer to the best that you could get, which is just a few millimeters. So we were happy with this. I'm also going to show you very quickly what happens when you increase the number of contacts. So again, here you're going to see the pose error changing as you increase the number of contacts. And as you can expect, the more contacts that you add, the better your performance get, but also your variance. Usually, like if you look for all the other objects, usually the variance on possible poses just gets reduced because again, now because you have multiple contacts, there is less room for non-uniqueness. So your performance gets better and better over time, over more and more contacts, sorry. Okay, so that was good, but there is still room for improvement. And what we found out is that what is more hard for us is how do you go about non-uniqueness? Again, how do you treat those cases that two different poses are going to result in very similar local shapes? The second case that was also very important for us and it is worth bringing into attention is that because those algorithms are learning simulation only, there is a clear mismatch between the local shapes that we are getting from the sensors versus the ones that we are getting from simulation. So closing this gap is also something that would definitely require more involvement. And that is really crucial if you really want to be able to say that there is a clear connection between the images that you're simulating and rendering from objects in simulation to the ones that you're getting from your tactile sensor. Again, one way that we have tried to go ahead and solve some of these problems is providing distributions, not just single estimates, but there is still plenty of work that can be done in this direction. But finally, I think instead of trying to solve this problem only with tactile, what makes more sense is can you use other sources of sensing? If you were to have vision that can already narrow down where are the possible poses of the object, then maybe non-uniqueness would be less important because you have all these other sources of information that are narrowing the set of poses that you should actually be considering. So this is definitely something that we want to explore in the future. But hopefully I have convinced you that this is a good way to tackle the problem of object localization, especially when there are contacts and you can make use of tactile sensing. And again, we are trying to solve this in a way that you have to be accurate, but you also don't rely on any previous data they have collected using the tactile sensor, which again is going to allow us to hopefully be more affordable and adaptable when you use this in a more bigger system. And this is exactly what I want to talk about now. I want to talk to you about kitting. Kitting is that type of system where you require accuracy. because you need to be able to place the objects properly. Another question is going to be, how do you solve kitting while being affordable and adaptable, but also trying to be accurate because you are demanded to be accurate. You have to place the object into the final location, which is specified. You don't have the, the luxury to be able to change it. And if you remember the first video that I showed you, this is a clear example of kitting. As you can see in here, the human just have boxes or bins full of objects. In this case, while there is clutter in each of the bins, the objects are all the same. Sometimes in kitting that's not the case, and you can have just a mixture of objects all in the same bin, and you also need to identify them. But for many cases, just to simplify the assembly, they usually do it in this way, where you have the same object in the bin, and then the goal of the person is pick that object and place it into the right location accurately. For us, it's going to look more something like this, where now we are using a Yumi ABB robot, which is precise enough for this task. And the goal is you have these objects and you have to pick one of them. Once you have picked it, you have to localize it. And the object is going to be inside the pick. So then is when tactile is going to be something that, again, is becoming important and very useful. It's something that you can actually use. And ideally, then you just want to go and pick it and place it, sorry. But that is something that often you won't be able to do because depending on how you pick the object, the actual place position of the object that maybe needs to go into this hole is actually the one that you're actually right now holding in your pick. So instead, what you probably need to do is, and what we are doing in this work is, we pick the object, we localize it in hand, but now we need to answer the question, do we need to regrasp it? Do we need to change the location of the object with respect to the grasp? If that is the case, then we will need to do one or several regrasps on the object until we get it into a configuration that then can be placed into the desired location. I'm going to insist on that. I think this is going to be adaptable because we are going to make a solution that can help, that can work for different objects and also different placing configurations, but also different clutter on how the objects are sorted in these initial positions. So this is going to make our system more adaptable. It's going to be affordable, and that is going to be very important for us. We want to make sure that we don't require data on the real system, and that once we are given new objects or new placing locations, the need for human expertise it's bare to minimum. So hopefully our system is capable to retrain or to improve itself so that it can handle any new object or any new requirement in terms of object placements or different clutter that you might see. We want it to be robust. That is something that I'm not going to go into the details into this talk, but ideally, if there is some change on the object position or if there is something that you are not accounting for, you would like to guarantee some certain performance, or at least be able to say that they have detected a failure. Sometimes just detecting a failure is better than just going ahead without realizing that something has happened. And finally, because kitting is demanding us to be accurate for the placings, we will need to come up with a solution that is forcing us to be accurate. So our solution in the end is going to be, let's do everything in simulation, but in a way that we can actually then be sure that it's going to transfer to the real world. The assumption is going to be the same as before. We're going to assume that we have access to the object models. That is something that some people may say, oh, in the real world, you might not always have access to the object model, and that is true. But we also believe that in many of the systems and tasks that we are envisioning this to be applicable for, having access to this object that you have already had to manufacture is not such a crazy idea. So we decided to start from here and see, okay, if we take this assumption that we know the object models, then can we bypass the need from maybe having to collect real data and just showing that it's possible to do all those things in simulation. So this is going to be an assumption. We're also going to assume that we know what is the desired configuration for the final placement of the object. And hopefully out of this assumption, what we are going to get is the ability to do all the learning of this solution self-supervised and in simulation. So that again, Once you give me a new object, I will be able to do kitting with it from the first attempt. You give me a new object, maybe you give me some compute time, but then you're good to go into the real system and pick and place accurately this object. This is how it looks in simulation. You first pick, you then localize the object, and now you go into the regrasps if they were to be needed. In this case, we perform one regrasp, and then we can place again. And this is how we are going to learn our system. We are going to keep doing these simulations, starting from different peaks, selecting different peaks, then seeing how much our localization is working or not, and again testing if our regraspings are successful or not. So now in simulation, we can just keep working and keep testing things until we are sure that our system is at the level that we want to be. Because if the performance in simulation is as high as possible, then your chances of transferring well to the real world are probably higher. So let me start with the first part. The first thing that you need to make sure is that you have a stable peak on the object. And we're going to learn this in simulation. There has been plenty of works on how to do this. I will describe later on which one we are trying, but basically from depth images, we're going to be able to select different grasps and then pick the one that works better for our task. Because it's important to know that when you're grasping an object, depending on how you're doing this, localization is going to be easier or harder, depending on, for instance, how non-unique is your local shape, but also depending on how many regrasps you're going to need to exert on the object in order to place it accurately. But by now, let's just say that for good picking, you will need to have this notion of how stable is your grasp. And the more stable, you are going to get the highest stability score, because we are going to kind of measure how well we are doing in each of those individual components. So from grasping, we are going to get this stability score. The next step, let me just first show you how this looks into the real system. So due to COVID, we couldn't finalize all the experiments, but we at least have some videos of how this will look like in practice. So in this case, we're taking a depth image. This is the red light that you're seeing. And from that red depth image, we can figure out, this seems to be a good grasp for placing this object. And this is exactly what it does. Once it detects what is the best grasp that it could do, it just goes and performs the grasp. Now that you have the object into your fingers, you want to localize it. You want to know where it actually is. And for that, we're going to use Tactile. And actually, we're going to use our word that I already explained before, where we are using tactile sensing to localize the objects from the first touch. As I already explained, this is something that can be done in simulation. You just have to learn a perception model for each of the different objects, but it's all learned in simulation. So there is, again, no need for you to collect real data. And what we are going to measure in this part of the work or this part of the system is something that we call the observability score, which basically is how much pose error you're encountering. And that's very related, again, to this non-uniqueness. Some poses are going to be very easy identifiable, so you're going to localize your object very well. Others, you're going to be unsure. So sometimes you might fail, sometimes you might be certain. And for those poses where there is more unclearness, you're going to have less observability. So your observability score is going to be lower. So observability score is going to be very related to how much pose error you will do, you expect to do, which again is linked to how much non-unique is your task. Why is this important? Why do we want to do tactile in here? Of course, we also want to add vision, but tactile is paramount, because imagine this situation. Just from vision, you cannot tell where is the object. You couldn't even tell if there is contact. I promise there is an object in there. It's just that you cannot see it. So that's why we really think that for this task, when you are starting to make contacts, tactile becomes really important. And the final part of this system is, now you know where the object is, can you tell me how to place it accurately? And for that, what we do is, I'm just going to go very quickly into how we are doing this. We are building a manipulation grasp. That what it does is, it takes all the possible grasps that we could do on the object and tries to link them if there is a possible way to go from one to the other. If you're grasping the object with one hand and then you could, with the other one, do another type of grasp on another part of the object, then those two grasps on the object are linked together. So you will put an edge on them. And finally, you add edges to those grasps that would allow you to place the object into its final configuration. And now at test time, you have the object in one initial grasp, and you just need to find the shortest path to get the object into the final configuration. And what we're measuring here is the manipulability score, which basically says how many regress do you need to actually go from your initial configuration to this final placing. And ideally, the less regress you have to do, the better, because the less error you are likely to accumulate over these manipulations. This is how it looks like. In this case, we are going to be giving ourselves the object to the robot in a position that we know. And now what it's going to figure out is, do I need to do any regress, or can I already place? In this case, you will see that it actually realizes that it needs to perform 2 regress on the object in order so that finally the object is good enough so that it can go and reliably take into account all the kinematics and possible errors that there could be, that it can finally go and place it into the desired configuration, as you can see. Okay, and I'm going back to picking, because picking is important. It's just that in this case, you want to make sure that you do it with awareness. You want to make sure that your picking solution, your final pick, is going to be good, not just for getting a good grasp, but also for getting the best performance on your task. And in that case, what we are asking is, how can we find those? And our solution is based on Dexnet 2.0, which is worked on at Berkeley from Jeff Muller and others. And basically what they do is they learn how to pick in simulation, but they do it in a very particular way. What they do is they take a depth image, then they propose several grasps on that depth image, and then they evaluate it. And that's the key thing. In their case, they only evaluate it to improve the stability. Can you find the grasp? Out of those grasps that you sampled, can you tell me, can you score them to get the one that is best? And once you have the one that is best, they just do it. How they train this? They train it in simulation. What they do is they generate plenty of depth images. They find possible grasp proposals. They score them in simulation, and then they can train this neural net that actually at test time, you just input it a depth image and gives you a score, following how you have trained it, the scores that you gave it in simulation. This is Dexnet that evaluates stability. In our case, and as you can already suspect, we are going to evaluate different things. We're going to evaluate how stable is the grasp, how much error you're expecting to do, so how non-unique is going to be your local shape, and finally, how manipulable is the location, the grasp that you're going to get, how much grasp are you going to need to go into the final localization. But the pipeline is the same. You just get a depth image, you find possible grasp on it just based on the point cloud, and then you score them based on some of those metrics to get a grasp that hopefully gets the highest score in all of them. And again, if you do this, because all of this is learned in simulation, you find a way to do picking that is task aware and that doesn't require any data beyond just what you do in simulation. This is an example. This is from a real a depth image from our system. If you just go for grasp stability, you're going to get this nice grasp on the object that is very stable. If you go for manipulability, actually grasping it on the edge is the perfect grasp, because then you can go and immediately place it, because this is the part that goes into the whole of the placement. So grasping it from here, it's in terms of manipulability, number of regress, the ideal grasp. This is very good and observable. This is a very unique pose of the object, because there is this kind of change between the two parts of the object. So again, if you grasp it from here, you get very high observability. But when you want to be good in all of them, you have to make trade-offs. And then our algorithm ends up with this one, which is manipulable. It's only going to need a regress. It's graspable. You can clearly say this is going to end up in a stable grasp. But it's also observable because there are some features in this part of the object that actually make it observable. So by combining all of them, you can get the best grasp that is going to be mindful about the whole task as it is. So right now we have only been able to prove that that is the case in simulation. We can find ways to find the best picking so that we can get high performance overall in the whole task. But the goal is to, as you have seen, we have already some initial steps into the real system. We just need to finalize them. So hopefully, as we can go more and more to the lab, we're going to have those final results soon. But I hope I have also convinced you that this should transfer to real. We have already tested all the components and they seem to work. So we hopefully have a solution that it's affordable because we can do this all in simulation, adaptable because we can handle different objects in different locations just by retraining or recomputing some of our components in simulation. It should be robust. Again, I'm not going to the details of this, but you can imagine that we can track the pose of the object over time. So there is room for being more robust to possible changes in the pose of the object or some unexpected events. And it's going to have to be accurate because otherwise they're not going to be able to place the object into the final configuration. So that's again implicit into the task itself. So I'm just going to basically finish here, but what is next for us is we definitely need to add vision. Systems without vision are not something that people is going to be interested in. We are working on that. We have different ways to combine it, but I just want to acknowledge that tactile alone is not the answer, and definitely vision needs to play a role. We are working into adding that. But I would say the other way, manipulation without tactile, I do believe it's missing something. You need to be able to reason about contact. Contact is going to be there all the time. Unknown objects, I already have mentioned this. By now, making the assumption that objects are known, that the 3D models is available, it's something that we think is reasonable enough. But there is always the question of why if you don't know the object, how many things can you still learn in simulation? How many things you will need to learn or retrain on the spot because now you're discovering the object as you're starting to manipulate it and try to solve these tasks. And finally, and that's something that really excites me, there is room in this system to make it reactive. What if I just go and move the object while the system is moving? Can we detect those changes? Can we react to them? Is our system good enough to take those into account? So those are things that I would definitely like to see. I'm gonna finish here. I hope I have motivated enough for you that good sensing is paramount for dexterous manipulation, but also that we definitely need to invest in what are the type of tasks that we are looking for. In our case, we went beyond picking, trying to also force ourselves to be accurate through placing. So thanks you very much. And if there is any questions, I'm very happy to take them now.
All right, thanks so much, Maria, for a great talk. We have a couple students in the call with us. We have Leon, Kim, and Edward Hu, who are fellow GRASP PhD students. If you're in the audience, there is a Q&A interface, so I definitely encourage anyone here to submit questions that they have, but maybe we can start with some questions that come from myself, Leon, and Edward. If Leon and Edward, if either of you two want to start first, please go ahead.
Okay.
Sure.
Okay. Okay, I guess I'll start. Or yeah, thanks. Okay, great talk, Maria. One question I have is, do you think you can go beyond just localizing the object that you're holding, such as if you're manipulating a screwdriver and it's in contact with a screw? And do you think you can basically estimate like some state about this screw through manipulation with the screwdriver through the touch sensor?
Actually, that's a very nice question. And there's some people in my lab that it's actually trying to answer the same question. In their case, they are not screwing, they're actually doing insertion. And what they're trying to understand is, can you say something about the hole where you're trying to insert your object? Let's say you know what is the object that you're holding, but then you, through the sensor, are trying to infer what are the forces, what is the type of contact that I am observing through the sensor holding this known object and trying to insert it. So how does the insertion region look like? And it's a hard problem, but they are starting to make some progress. And I think there is some signal data. I'm just not sure how many real data you're gonna need. So for how long are you gonna need to explore in data? So there's gonna be probably a trade-off between how much time you wanna spend trying to understand how it looks like, the region that you're trying to actually do the insertion in their case, or in your case with a screw, how much you can actually get from the screw versus maybe just in this case, adding some extra perception, like maybe vision, or just maybe even trying to touch it by yourself, rather than trying to do it in such an indirect way. But I think it's a very challenging question. And sometimes you don't have the luxury to, again, add this extra perception system. So there might be room for that. And I think there is hope that there might be extra signals through the forces that the sensor is capturing that can give you some clues on what's going on. And I especially think that for screwing, that's a task that I really like and that I've been thinking on for a while. So I do think that maybe just by detecting the forces when your tool is sleeping, when it's actually sticking, so that you can infer something more, so that you can actually solve it easily. So I think the answer is yes, but how to do it properly, that's, I think, very open for research.
So I have a question. So I think there's been a lot of like really great results recently that have combined simulation and learning in some way. And I think, you know, everyone does it in their own particular way. It's a little bit different. And one distinction that I find myself making is whether simulation is used in some way, something like pre-training, where you extract knowledge about the simulator, extract it into a neural network or something, and then use that neural network alone online. And there are other methods that sort of use simulation and learning at the same time in tandem. And maybe an example of that, maybe thinking of like the work that you did with Anurag back in 2018. Can you speak maybe to this project in particular, but also maybe generally, if you have any philosophical thoughts about how you make that design decision about which of the two that you do?
Yeah, again, I like this question a lot, and I don't think I have one answer to that. I think many times this is very task dependent. How expensive is it going to be to simulate your task in the real time? If the system is simple enough, like in the case of pushing, you have that luxury where you can actually go into your system or into your simulator and say, hey, what is it going to happen next? Give me some starting points, so then I can just maybe do a correction based on my learning. Other cases that are more complex, I think you don't have that luxury to go and ask the simulation at running time. So that having a policy or a model that is fast enough to query might be the best solution. Like imagine you have to simulate fluids. You of course cannot do this in real time. So there are definitely trade-offs that are very task dependent. And in the end, I think for most of us, you want to understand your task. Um, Once you understand your task, you will know more about this, so you can do a more informed decision. I think for kitting, because the tasks are, let's put it this way, once you have the depth image, you already have plenty of information, so that it probably doesn't make a lot of sense to try to simulate something there. You're good to go with that. And we're also making some assumptions that maybe simulation will actually be useful for. We're actually assuming that when you do the regress things, the kinematics are going to hold and we are not going to get big motions that are unexpected between the objects. So you are sticking here and you do another grass, the object will keep sticking. Those are big assumptions that probably just prevent us from even using a simulation. But if that were to be the case, if there were to be not the assumption that things are going to stick, but that things might just be more dynamic, then having something that tells me, oh, when you do this motion, this is the most likely outcome of the final pose, then I think that it would make a lot of sense to add simulators. So that maybe you just have to learn on the fly the reminder, oh, I did this once, and this was my prediction from the simulation, how the object would move, but actually move this way. Can I just add the what is missing? But again, I think that depends on how fast can you simulate things for your task. But if you have those, I would use them if they are good enough. In the end, I think there is a lot of theory saying if your prior model is good enough, it's going to help you. If your prior is not good enough, it's just going to be worse than just no prior. And if you have enough of data, you won't need a prior at all. So again, it depends a lot of what you can assume on your task.
Right. That is a testament to how how complex these sorts of decisions that on a cursory glance look like they're very much so in the weeds or like not very different. But yeah, I agree. There's definitely like a lot of things in a specific problem setting that can affect what's going to actually be feasible. Yeah. Do we have any other questions?
I can go one more. No one else has it. So like in the current kitting example you give, it seems like the place is not hard to execute. It seems like you just have to like put it down into like a hole. And I was wondering, like back to the screwing example, like if you're assembling furniture, you probably have to do some more complex placing motions. So I was wondering if, yeah, you have like thought about doing like complex placing, I guess.
So the farthest I've been looking into is how do you assemble multi-objects in this case, we're placing into an static scene. And it's true that in this case, it's just lifting. I mean, in the end, when you think about placing, unless you try to place it in a very weird manner, most of the placings are going to look something like that. Where as long as you have the good configuration, just a matter of then either going down or going to some locations, and that you can solve with some kinematic planner. But I agree that if you wanted to assemble a furniture in IKEA, then the task becomes much more harder. Also because there are many less constraints. Like sometimes you have to put something on the floor, so then you can put something on top. And then the first question that you need to ask is, or the answer is, how do you place this in a stable way? Okay, that's fine. Maybe you know that this is flat, then you can do this, but then you need to start reasoning about multiple objects at the same time. And for me, this is multi-object assembly. And I really want to see this happening in our system. I've been already trying to think, okay, maybe I have not a screw in, but just a bolt and another a screw, and you just want to insert them, something like that. Then you have multi-object. And that becomes much more tricky because, and I think that's going back to the first question, then there's going to be those interactions with these two objects that you're only going to be able to sense between your tactile sensors, maybe some vision. And that complicates a lot the problem. Because when things become, when forces start playing a role and there is dynamics, then just poses are not going to be enough. And we need to find ways to represent those forces and those other types of interactions that go beyond just how the objects are located inside your hands. And that's something that I'm also looking forward to. It's a bit more unclear what is the right path to follow. And I think that what's make that manipulation different from other types of robotics, and especially from computer vision. That there are many things like forces, wrenches, torques, that we don't have even a good vocabulary to talk about them. So then how do you represent and how do you use them? How do you exploit those becomes even harder. But I think that's also the right way to go. So we are starting with this task, which is placing, which already asks us some accuracy. But then when we add some extra pieces like forces and dynamics, accuracy will be one of the questions, but there are going to be much more challenges to solve in between. But I also think that's the right way to go. So it's in our minds how to solve multi-object assembly, but there's going to be not just poses to play a role. Then we are going to probably need to estimate what are the forces and how they are playing within each other.
I think IKEA furniture assembly is such a great example,
Yes.
particularly when your furniture is made out of flimsy, medium density fiberboard, and you need to worry about the materials breaking as well, which going back to using simulation, you're going to have a hard time finding a simulator that's good at like real-time assessment of whether or not you're treating your materials well. Yeah.
And when you go into the formable objects, and the world explodes. The type of task that you can try to solve that is just crazy. And that's why I think that humans are still going to play a big role in assembly, just because there are many objects that even how to represent them properly is just such a big question in research. But I also think it's exciting that we are getting closer to those one step at a time.
Great. Well, thanks so much for coming out, Maria. This was a really fun talk. And thanks everyone for coming out and attending and listening. And I encourage you all to reach out to Maria if you have any additional questions.
Please do. Thanks a lot, Matt, for having me here. It was a pleasure.
Glad to. Take care, everyone.
Bye-bye.